Welcome to yet another session in electrochemistry. After learning the laws of electrolysis, in this session we will be considering another aspect of electrolysis, namely the products of electrolysis. At the end of this session, you will be able to predict the products of electrolysis given the electrodes and the electrolytes. Let us take up one by one. First, I am going to write molten copper chloride. Molten copper chloride. That means copper chloride in a molten form or fused state, so that it can pass, the ions would be able to move and pass current. And the electrodes would be inert electrodes. I'll write with inert electrodes. What are the inert electrodes? Commonly, these are graphite or platinum electrodes. And why are they called inert electrodes? Because the electrodes do not interfere or react with the ions in the electrolyte. Now the two ions available in the electrolyte are only Cu2 plus ions and Cl minus ions. So there is no problem. You will be able to write the reactions at cathode and anode. Go ahead and write the reactions. So you have copper ions moving to the cathode and getting discharged as copper solid, and at anode chloride ions give up the electron and form chlorine gas. You have to write here aqueous. So this is quite simple. Next we will take up aqueous copper chloride. We are taking copper chloride dissolved in water with inert electrodes. We have copper ions, chloride ions, and also H plus ions and OH minus ions. When we pass current through this solution, copper ions and H plus ions move to the cathode. When there is more than one ion moving to an electrode, there is competition between the two ions to get discharged. Which one would succeed and what is the rule applied? That is what we are going to see. Now when I say H plus ion moving to the cathode and getting reduced, it would be more correct to consider water as a whole and getting reduced at the cathode, because the concentration of H plus ions and OH minus ions as it is in water is very low. Let us write the equations for the two reductions at cathode. Cu2 plus aqueous plus 2 electrons giving Cu solid. Okay, I'll write at cathode. For water, we have to write H2O liquid plus electrons to give H2 gas plus OH minus ions. This is how we have to write the equation for reduction of water. Let us balance. We have to write 2 H2O liquid taking up 2 electrons to give H2 gas plus 2 OH minus ions. Now the E naught for this, electrode potential for this, is 0.34 volt, and E naught for this is minus 0.83 volt. The rule that applies here is the one which has higher reduction electrode potential will get reduced. Okay, so higher reduction electrode potential, that is the criterion here. So obviously it is copper which will be discharged. So copper succeeds in getting discharged at the cathode. Now let us consider the two anions. The two anions are OH minus and Cl minus move to the anode. Right, write the reaction for that, and as I said before, we have to consider the oxidation of water as a whole and not that of OH minus ion. So Cl minus ion will form half Cl2 gas, giving up that electron, and for water oxidation would be H2O liquid, giving 2H plus half O2 gas, 2H plus aqueous plus half O2 gas plus 2 electrons. Let's write the electrode potentials for this. E naught for this, for the chloride ion to get discharged as chlorine gas would be 1.36 volt, and for oxygen E naught is 1.23 volt. Here the criterion that is applied is the one having lower reduction electrode potential. At cathode it is the one which is having higher reduction electrode potential, and at anode it is the criterion is the ion which has lower electrode potential would be discharged. When you look at the values of the two equations, you see that water has lower electrode potential and oxygen should be the product at the anode. But here, that due to certain factors, actually the voltage that is required to discharge O2 gas is much higher than what is given by the E naught value due to the interaction of the oxygen gas with the surface of the electrode and other factors. We need to have higher potential, higher voltage to discharge oxygen gas. This is called over voltage or over potential. You can just give it as the reason due to over voltage or over potential. It is the chlorine gas. Actually, to discharge oxygen gas from this, you will be needing more than what you need to discharge the chlorine gas. Hence, chlorine only will be obtained as the product. I will write here, this is the one that is correct. So, chlorine is the product. Is that clear? So, when we pass electricity through copper chloride solution, I will write CuCl2 and H2O. When you electrolyze, the products are Cu at cathode and chlorine gas at anode, and water is still remaining in the electrolyte. Is that clear? We have seen the competition between the two ions at cathode and anode, and we have learned the rule to be applied to get the product at the cathode and anode. And here you see there is, when we say the rule itself, we mention the contradiction. Here we have learnt the reason why oxygen is not released as per the rule but chlorine is released. You have to keep in mind, you have to state the reason as over voltage or over potential. And if you observe, the products are the same when we electrolyze molten copper chloride and aqueous copper chloride. Bear it in mind, there is no change in products in the case of molten and aqueous copper chloride. Next one to be taken up is electrolysis of fused NaCl. Fused NaCl with inert electrodes. Write down the ions present, Na plus and Cl minus. And I am sure you will be able to write the reactions at anode and cathode. For the sake of completion, I am writing them here. At cathode, Na plus aqueous, taking an electron to form Na solid. Half Cl2 gas as an electron. When you take aqueous NaCl, that is sodium chloride in water, with and pass current with graphite or platinum electrodes, let us see what would be the products. Write the ions present: Na plus, Cl minus, H plus and OH minus from water. Right, now it is Na plus ions and H plus ions moving to the cathode, and as before we have to consider the oxidation reduction of H plus ions as the reduction of water as a whole. When we write the equation Na plus and water, now you will be able to write equation for the reduction of water also. 2H2O liquid plus 2 electrons giving H2 gas plus 2OH minus, aqueous. Okay. Now the values for them are Na plus, this has a value for E naught as minus 2.71 volt, and the E naught value is minus 0.83 volt. What is the rule we applied? We said the one having higher reduction electrode potential would be discharged. It is water which has a higher value, so water would be reduced in preference over Na plus, and the product would be hydrogen gas, right? So this is the one that will be taking place. Regarding the reactions at anode reactions, you have the same Cl minus ion and OH minus ions, so it is going to be the same as before. In the competition between the Cl minus ion and OH minus ion, though as per the value water must get oxidized, releasing oxygen gas due to the over voltage or over potential of oxidation of water, chlorine gas is released. Okay, so the product is Cl2 gas. Now when we write NaCl plus H2O, the products of electrolysis are H2 gas plus Cl2 gas, isn't it? Cl2 here, the anode, the product is Cl2. You can refer to the earlier reaction, Cl2 gas and hydrogen gas at the cathode, and you have NaOH. So to balance, you have to have so this is the reaction for electrolysis of sodium chloride, aqueous sodium chloride solution. Actually, this is the reaction that is used in the electrolytic cell to produce sodium hydroxide. For producing sodium hydroxide on a large scale in an electrolytic cell, we use brine or aqueous sodium chloride solution, and sodium hydroxide is manufactured, which is industrially a very important chemical. It is manufactured or produced on a large scale, and the byproducts are H2 gas and Cl2 gas. So this is the fourth one we have considered, aqueous electrolysis of aqueous NaCl. Next thing to be considered is electrolysis of sulfuric acid with platinum electrodes. Here there are two cases: dilute sulfuric acid and concentrated sulfuric acid. The ions present are H plus and sulfate ions. H plus ions from and OH minus ions from water. At cathode, whether it is the reduction of the H plus ions from sulfuric acid or the reduction of water, the product is going to be hydrogen gas, you know. So we will write the reaction at cathode as H plus aqueous taking an electron to form half H2 gas. At anode, the sulfate ions could oxidize. If the sulfate ions get oxidized, you get the disulfate 2 minus ion plus 2 electrons, or water can be oxidized, which will form half O2 gas and H plus ions. The E naught for this the first reaction is 1.96 volt and E naught for the second one is 1.23 volt. And you know that oxidation of water requires more than requires an voltage which is more than what is shown by the E naught value, but it is still less than what is required to oxidize the sulfate ion. So water can get oxidized in this case to form oxygen, and particularly when it is dilute sulfuric acid with water in excess, the second reaction would be the appropriate reaction taking place at the anode, and then oxygen would be the product. So this is for dilute sulfuric acid. At the same time, if you have concentrated sulfuric acid, this one would be the correct reaction for the anode, and the product will be the S2O8 2 minus ion. This will be the reaction for concentrated sulfuric acid. I suppose it is clear. In the case of electrolysis of sulfuric acid with platinum electrodes, at cathode we have H2 gas, and at anode we have O2 gas in the case of dilute sulfuric acid, which is the same as electrolysis of water in the presence of acid, isn't it? When we electrolyze water, we have to add a few drops of acid and you get H2 gas at cathode and O2 gas at anode. It would be the same as electrolyzing very dilute sulfuric acid. In the case of concentrated sulfuric acid, the products would be H2 gas at cathode and the S2O8 2 minus ion at the anode. So far we have been considering electrolysis of different electrolytes with inert electrodes. You know the products of electrolysis of aqueous copper chloride with platinum electrodes. Let us electrolyze aqueous copper chloride with copper electrodes. The ions are Cu2 plus, Cl minus, H plus and OH minus. At cathode, the two ions that would be competing for reactions would be copper ions and H plus ions, and you know the values of E naught values of the copper ions and that of reduction of water, and obviously the copper ions having higher reduction electrode potential would be discharged at the cathode. I don't have to explain once again, it's very clear to you, already we have discussed it in a few cases. At anode, in addition to chloride ion and OH minus ion or oxidation of water, we have a reactive electrode here. That is what we have to keep in mind. We have a reactive electrode, it's not inert. Now when we have only chloride ion and the hydroxide ion, or I would take it as oxidation of water, we saw that water has lower electrode potential than chloride ion, but still chloride ion would get oxidized to form chlorine gas due to over voltage. All that stands good, and you know the value for this is 1.36 volt and for this it is 1.23 volt. Now when the copper ions get oxidized, to form copper atoms from the electrode get oxidized to form copper ions. That has an E naught value of 0.34 volt. Now you see at anode the criterion is the one having the lowest electrode potential value, and so naturally it is copper to get oxidized to form copper ions requires the lowest E naught value, and hence this should be the reaction at the anode. So the reaction at cathode is copper ions taking up electrons to form copper atoms, and at anode copper atoms from the electrode going into solution as copper ions. Do you remember the electrorefining of copper? In electrorefining of copper, which you have studied in connection with metallurgical operations, see, anode we use impure copper. We take impure copper as anode and a pure strip of copper metal as cathode, isn't it? And then we take any one of the electrolytes, copper sulfate or copper chloride, for the electrolysis, and from the electrolyte the copper ions move to the cathode and get deposited, and from the anode copper ions go into solution as copper atoms go into solution as ions, because the other elements present with copper are less reactive. So we can write the reaction as Cu2 plus 2 electrons to form Cu at cathode. That's what you have learnt, and then at anode it is Cu solid forming Cu2 plus, isn't it? It is the same as the products that we have arrived at by taking into consideration the electrode potential values. Is that clear? So there is no difference between the two products. Only thing is our approaches were different. Now we have to remember that when the inert electrodes are involved, we have to consider only the competition between the ions, but when we have a reactive electrode in the place of inert electrode, we have to consider the oxidation of the electrode also at anode. What would be the products of electrolysis of aqueous silver nitrate with platinum electrodes? Write the ions Ag plus, NO3 minus, H plus and OH minus ions. The two cations are Ag plus and H plus are reduction of Ag plus or reduction of water at cathode. The E naught value for aqueous Ag plus to get reduced to silver atoms is 0.80 volt, and you know the value for water, reduction of water, E naught value is minus 0.83 volt. So the product is silver metal at cathode. At anode you have NO3 minus ions and oxidation of water. Now oxidation of water requires 1.23 volt as per the E naught value, but you know that due to over voltage it requires a higher voltage higher than this for oxidation, but still the voltage that is required for the oxidation of water to oxygen is less than what is required to oxidize NO3 minus ions. Hence the product would be only oxygen by the oxidation of water at anode. So we can write the equation which we always write for oxidation of water. So what are the products of electrolysis of aqueous silver nitrate with platinum electrodes? Silver at cathode and oxygen at anode. The next one would be electrolysis of aqueous silver nitrate with silver electrodes. The ions are the same, Ag plus NO3 minus, H plus NOH minus, and at cathode also the reactions are going to be the same. It would be, you have to consider the reduction of Ag plus ion or reduction of water, and as per the electrode potential values it should be silver which should be discharged at the cathode. When we consider the anions NO3 minus and oxidation of water instead of OH minus ions, the values, as per the values we already saw that it would be only the oxidation of water which will be taking place at the anode. And compared to that, when you have the silver metal going into solution as Ag plus ions, this is going to require only 0.80 volt. So in comparison with water which requires 1.23 volt or little more than that, the E naught value required for the oxidation of silver is going to be much much lower. Hence at anode the reaction that should be taking place must be the oxidation of the silver atoms from the electrode to silver ions. Is that clear? So the reaction at cathode would be, let me write now separately, at cathode it would be Ag plus aqueous to form Ag solid, and at anode Ag solid forming Ag plus aqueous plus an electron. Is that clear? So whenever you have the electrolysis of any electrolyte with the same metal as that of the electrolyte, the reactions are going to be like this only. That is, the ions of the electrolyte, cations of the electrolyte getting discharged at the cathode as atoms, and the same atoms from the anode material going into solution as ions. That would be the same. I suppose you have got a complete idea about the products of electrolysis of different electrolytes using inert electrodes or reactive electrodes. Thank you.